Hello there, and welcome to the Sleepy Space Channel. Tonight, we are turning our gaze toward Andromeda, the nearest great spiral galaxy, a slowly turning wheel of perhaps 1 trillion stars, hanging in the dark, just close enough to call a neighbor. Its light has been traveling toward us for 2.5 million years, older than our entire species, crossing the quiet of intergalactic space without hurry. You can see it with your own eyes on a clear, dark night, a faint and patient smudge, asking nothing, offering everything. We will drift across its dust-laden disk, into its quiet double center, and out through a halo so wide it nearly grazes our own. 100 gentle facts, carried slowly across the dark, just for tonight. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Allow your eyes to grow heavy and let the day fade quietly away. Let's begin. There is something in the night sky that has always been there. Long before anyone thought to name it, long before any human mind had the words for what a galaxy was, the faint smudge of Andromeda hung in the dark above every civilization that ever looked up and wondered. It did not announce itself. It did not flare or pulse or demand attention. It simply remained a soft, elongated blur in a corner of sky that most people would walk past without a second thought, tucked between the familiar patterns of stars, patient and faint, and impossibly far away. Andromeda is the nearest large spiral galaxy to our own. When astronomers speak of it in numbers, those numbers are almost too large to hold in the mind gently, so perhaps it is better to let them arrive slowly. It lies approximately 2.5 million light-years away. A light-year is the distance light travels in a single year, and light moves at about 300,000 kilometers every second, which means in 1 year it covers a distance that is already far beyond anything we navigate in daily life. Now take that already enormous span and multiply it by 2.5 million. That is the distance between where you are lying right now and the edge of Andromeda's outer glow. And yet, on a clear night, far from city lights, you can see it without a telescope. You can hold out your hand and find it somewhere near the constellation that shares its name, and there it will be a faint thumbprint of light, barely brighter than the sky around it, easily missed, easily mistaken for a wisp of thin cloud. But it is not cloud. It is an entire galaxy. It is 1 trillion stars. It is 2.5 million years of traveling light, arriving quietly in your eye on an ordinary evening. That light has been traveling since before our species existed. The photons that land softly on your retina tonight left Andromeda roughly 2.5 million years ago, when the Earth was a different world entirely. Our ancestors were not yet what we would recognize as human. There were no fires built by intentional hands, no spoken languages, no names for anything above or below. The universe was already enormously old by then, already more than 11 billion years into its slow existence, and Andromeda was already a mature, settled spiral galaxy, spinning in the dark the way it still spins now. It sent its light out in all directions, the way light always does, and some fraction of it began the long journey toward a small rocky planet that would eventually develop eyes. 2.5 million years later, those photons arrive. They enter a universe that now contains people lying in beds, breathing slowly, listening to a quiet voice tell them about the place that sent the light in the first place. There is something deeply comforting about that, if you let it settle. Andromeda belongs to a group of galaxies called the Local Group. This is the name astronomers give to the family of galaxies that share our general region of the universe, not neighbors in any human sense, but gravitationally associated, bound together by the slow and enormous pull of accumulated mass. The local group contains a few dozen members, most of them small and dim, dwarf galaxies that orbit the larger ones like distant companions. The two giants of the group are our own Milky Way and Andromeda. They are the anchoring points around which all the smaller members tend to cluster. In this sense, Andromeda is not a stranger. It is family in the loosest and most cosmic sense of that word. It is the largest sibling in a family of galaxies scattered across a few million light years, each one moving according to the slow grammar of gravity, each one containing more stars than there are grains of sand on any beach you have ever walked. Andromeda itself contains approximately 1 trillion stars. That number is offered not to overwhelm, but to let it drift past, like something you might see through a foggy window, large and soft, present but not pressing. 1 trillion is a number our minds were not built to hold in full, and that is all right. You do not need to count them. You only need to know that when that faint smudge appears in the sky, the light you are seeing is the combined, blended glow of something like 1,000 billion individual suns, each one burning with its own slow fire, most of them circling that galaxy the way the Earth circles ours, each one separated from its nearest neighbor by distances so large that the space between them feels more like everything than something. The Milky Way, by comparison, contains perhaps 300 to 400 billion stars. Andromeda is, by this measure, a somewhat larger galaxy than our own, though the comparison is uncertain, complicated by how you measure mass and where you draw the edges. Both galaxies are enormous. Both are spirals. Both rotate. Both have central regions dense with ancient stars and outer regions scattered with younger ones. From a distance, an observer in some third galaxy far away might look at both of them and see two similar wheels of light, separated by a gap that seems small only on the grandest of scales. We live inside one of those wheels, looking out at the other. That is the situation. That is where you are tonight, as you close your eyes and let the voice carry you. You are inside one great spiral of light, somewhere near its edge, on a small, rocky world around a medium-sized star, sending your attention across 2.5 million light-years of mostly empty space toward the nearest great wheel that resembles home. Andromeda is not a distant and alien thing. It is, in the context of the universe, extremely close. Most galaxies are so far away that no individual star within them could ever be resolved, no structure discerned without the most sophisticated instruments. Andromeda is close enough that we can study it in extraordinary detail, close enough that its individual star clusters can be catalogued, its dust lanes traced, its internal motion measured. It is the galaxy we know second best, after our own, and even that ranking is contested, since our position inside the Milky Way makes certain things harder to see than if we could step outside and look at it from far away. There is something gentle about Andromeda's visibility to the naked eye. In a world full of things that require technology to perceive infrared sensors, radio receivers, gravitational wave detectors, Andromeda simply hangs there in the dark, available to any eyes willing to let themselves adjust. You do not need a degree in astronomy. You do not need a telescope. You need a dark sky and a moment of patience, and the galaxy will find you. The sky does not present Andromeda as an event. It offers no announcement, no dramatic brightening, no signal that you should pay attention. It is simply there, a soft presence that has always been part of the dark overhead, noticed by some, missed by many, indifferent to the difference. In that quality of quiet availability, there is something almost kind. The universe does not always make itself easy to find, but Andromeda is there, visible and faint, and enormously patient, the way the best companions tend to be. And so we begin to look more carefully, letting the faint smudge come into focus, not suddenly, not with any rush, but in the way that understanding often comes slowly, gradually, one layer of detail revealing itself after another, until the blur becomes a structure, the structure becomes a system, and the system becomes something almost imaginable if you hold very still and let your mind stretch gently in the direction of 1 trillion distant suns. The first thing to understand about Andromeda is its shape. It is a spiral galaxy, one of the most common forms of large galaxy in the universe, and one of the most beautiful, if beauty can be said to belong to something no individual human will ever see whole with unaided eyes. A spiral galaxy is a flattened disk of stars, gas, and dust, organized by rotation into a structure of arms, curling outward from a central bulge, like the pattern cream makes in a slow cup of coffee, or the shape of a pinwheel left out in a very gentle wind. More precisely, Andromeda is classified as a barred spiral galaxy, meaning that at its center there is a bar-shaped concentration of stars from which the spiral arms extend. This bar is a structural feature found in many spiral galaxies, including our own. It is not rigid in any ordinary sense. It is made of billions of stars orbiting in coordinated patterns, maintained by gravitational resonance, like a standing wave in a very slow medium. The bar rotates with the galaxy, and the arms sweep outward from its ends, and the whole system turns in a way that, if you could watch it from above, would look like almost no movement at all. Andromeda's disk, the bright, star-filled flat region visible in images, extends more than 100,000 light-years across. This is the number that captures the sense of it, 100,000 light-years from one side to the other, in just the region bright enough to see in optical light. The full extent of the system, including its outer halo and diffuse extensions, reaches considerably further. The disk is thin relative to its width enormously, almost absurdly thin, like a sheet of paper compared to a dinner plate, and within that thin disk, the density of stars and gas and dust is high enough to sustain ongoing star formation, ongoing stellar death, ongoing slow chemical evolution. Before astronomers understood what galaxies were, Andromeda was catalogued as a nebula, one of many fuzzy patches in the sky that did not resolve into individual stars through the telescopes of earlier centuries. It was listed, studied, wondered at, and debated. Some thought these nebulae were gas clouds within our own galaxy, perhaps nurseries for future solar systems. Others suspected they might be entire separate star systems, enormously far away, what one philosopher had called island universes, borrowing a phrase that captured something true before the instruments existed to confirm it. The debate was settled only in the early 20th century, when astronomers were able to identify a specific type of star within Andromeda, a pulsating star whose brightness varies in a predictable rhythm tied to its true luminosity. By measuring how bright this type of star appeared, and comparing that to how bright it should be, astronomers could calculate the distance. The answer was far beyond anything the galaxy's edge theorists had proposed. Andromeda was not a nearby gas cloud. It was a separate galaxy outside the Milky Way, at an enormous distance. The universe was suddenly much larger than it had been the day before. This realization that the Milky Way was not everything, that the faint nebulae scattered across the sky were each a separate island of stars beyond reckoning, is one of the quietly enormous moments in the history of human understanding. Not a crisis, not a drama, but a slow expansion of the frame. The universe grew, overnight, by an almost inconceivable amount. And Andromeda was at the center of that expansion, the specific fuzzy patch whose distance first demonstrated how large everything actually was. When you look at Andromeda in the sky, you are not seeing it face on. You are seeing it at an angle, tilted roughly 77 degrees from your line of sight, which means you are seeing something close to its edge, an elongated ellipse of light, not the grand face-on spiral it would appear to be from above. The full, sweeping structure of its arms, the open pinwheel shape, is almost entirely hidden from this angle, compressed into an elongated glow. This is one of the small ironies of having Andromeda as our nearest galactic neighbor. We can see it with the naked eye, but we cannot easily see its shape. To appreciate Andromeda's spiral arms, you need infrared or radio observations, or images carefully constructed to reveal structure, or simply the willingness to mentally rotate the galaxy and imagine it as it would look from a perpendicular vantage. Even from our tilted view, its disk structure, its central bulge, and the darker lanes of dust running through it are visible in detailed photographs. But the full spiraling sweep of it, the way its arms arc outward from the bar at the center, curving and thinning into the outer disk, that requires something more than what the naked eye can offer. Andromeda is likely somewhat more massive than the Milky Way, in terms of stellar content, though the comparison is genuinely uncertain. Our galaxy has a more active star-forming region and a somewhat different gas distribution. The two galaxies are, in cosmic terms, very similar spiral galaxies of comparable size and structure, born around the same epoch in the universe's history, evolving in parallel, each surrounded by their own family of satellite galaxies, each spinning in the dark, with their own set of globular clusters and dwarf companions and extended halos of dark matter. The local group that contains them both is, in the context of the wider universe, a quiet backwater. There are clusters of galaxies that contain thousands of members, enormous concentrations of mass generating their own local gravitational fields. The local group is small, by comparison, a few dozen galaxies, 2 large spirals, the rest small and faint. But small is relative. The entire local group spans several million light-years, and within that span, everything is moving, everything is pulled toward everything else, and the two great spirals at the center, the Milky Way and Andromeda, are slowly, almost imperceptibly, being drawn toward each other. This is not urgency. This is not a crisis. This is the ordinary, slow business of gravity on cosmological timescales, playing out across spans of time that make all of human history feel like a single heartbeat. The approach between our galaxy and Andromeda has been ongoing for billions of years, and it will continue for billions more, and during that entire span, nothing about the night sky will change noticeably, not from the perspective of any human lifespan, not from the perspective of any civilization. There are also smaller galaxies associated with Andromeda satellite galaxies in orbit around it, just as smaller galaxies orbit the Milky Way. The most prominent of these are known as Andromeda's companion ellipticals, large enough to be visible in telescopes, old enough to have exhausted most of their star-forming gas billions of years ago. There are dozens of known satellite galaxies around Andromeda, many of them tiny and dim, containing only millions or tens of millions of stars. They orbit at various distances and inclinations, each one a gravitationally bound companion, each one slowly being pulled and shaped by the enormous mass of the galaxy it circles. The concept of a galaxy having satellite companions is something that applies to most large galaxies. Our own Milky Way has the Magellanic Clouds, two irregular galaxies visible only from the southern hemisphere, bright enough to be seen easily with the naked eye. Andromeda has its own set of companions, less visually dramatic from our vantage point, but present in images as faint patches of light near the main galaxy. They are part of the extended system, part of the gravitational family, and their presence speaks to a long history of smaller galaxies being drawn in and incorporated over time. Dark matter, too, shapes Andromeda in ways that are invisible but essential. The stars and gas and dust that can be seen in optical images are a small fraction of the total mass of the galaxy. Most of the mass is invisible, not because it is hidden in shadow or obscured by dust, but because it does not interact with light at all. It is dark matter, a component of the universe whose nature remains one of the genuine open questions in physics, a substance that exerts gravity but emits no radiation, reflects nothing, absorbs nothing. Its presence is inferred entirely from its gravitational effects. Without dark matter, galaxies like Andromeda would not hold together. The stars in the outer regions of the disk move faster than they should if only the visible mass were pulling on them. The galaxy would fly apart if the gravity of visible matter were all there was. Dark matter provides the additional pull that keeps everything orbiting, keeps the disk coherent, keeps the satellite galaxies in their orbits. It is the majority of Andromeda by mass, though its distribution is invisible to every kind of light we can detect. This invisible scaffold surrounds the galaxy in a roughly spherical halo extending far beyond the visible disk, and it is in this halo that much of the galaxy's true mass resides. When you look at Andromeda as a faint smudge in the night sky, you are seeing only a tiny, luminous fraction of what is actually there. The true extent of the system is much larger, much dimmer, and mostly dark. And so, the point of light becomes something larger, not suddenly, but gradually, as if it has always been waiting to be understood. A smudge becomes a disk becomes a spiral becomes a system, with mass and history and companions and invisible structure extending far into the space around it. And this is only the beginning of what Andromeda is, seen from the outside. Everything in Andromeda moves. This is worth saying, even though none of the motion is visible to the eye, and none of it will become apparent in any human time frame. The entire galaxy rotates a vast, slow turning of hundreds of billions of stars around a common center, each star following an orbit shaped by the collective gravity of everything around it. The rotation is differential, meaning the inner parts of the galaxy complete their orbits more quickly than the outer parts, and this differential rotation is one of the things that generates and maintains the spiral structure visible in images. Spiral arms, it turns out, are not fixed structures. This is one of the more quietly interesting things about spiral galaxies. The arms are not like the spokes of a wheel, attached at the center and turning with it. If they were, differential rotation would wind them tighter and tighter over time until they disappeared. Instead, spiral arms are density waves, regions of space where gas and dust and stars are slightly more compressed, moving through the disk the way a wave moves through water, while the water itself stays mostly in place. Imagine a slow, circular traffic jam on a very large road. Cars pile up at a certain point, move slowly through, and then continue. The jam itself stays in one place while the individual cars pass through it. Spiral arms work somewhat like this. They are regions where the material of the disk slows and compresses slightly, spending more time there before moving on. New stars form in the compressed regions because the density is high enough to trigger collapse in the gas clouds. As the wave passes, those newly formed stars move out of the arm and continue their orbit while the wave itself persists in place. This means the stars you see in a spiral arm today are not the same stars that were there a billion years ago. The arm is a pattern, a slow wave of slightly increased density, and the stars within it are passing through, not residing in it. The galaxy is less like a fixed structure and more like a slow, self-maintaining pattern, a form that persists not because its parts are fixed, but because the process that creates it is continuously ongoing. Andromeda's spiral arms are dusty and complex. They contain lanes of cold molecular gas, regions of ongoing star formation, clusters of young and bright stars illuminating their surroundings, and dark channels where dust blocks the light of stars behind it. In optical images, these dust lanes appear as dark ribbons threading through the brighter glow of the disk, not absence, but presence. The presence of cold material dense enough to absorb the light coming from behind it. Dust in galaxies is not the same as household dust. It is made of tiny solid particles, grains of carbon, silicates, and other materials produced in the outer atmospheres of aging stars and scattered through the interstellar medium. These grains are extremely small, but there are so many of them across so many light years of disk that their combined opacity is significant. They absorb and scatter light at certain wavelengths, particularly blue light, which is why distant regions of a galaxy often appear redder than they would if viewed through empty space. Infrared light passes through dust more easily than optical light, and infrared observations of Andromeda reveal a different layer of its structure. In infrared, the warm dust itself glows, tracing the spiral arms in heat rather than in reflected starlight. The result is a view of the galaxy that emphasizes its thermal structure, the regions where energy is being absorbed and re-radiated, where star formation is heating the surrounding material from within. These views show a ring of dust and star formation, particularly prominent in Andromeda's disk, a broad ring-like feature roughly 30,000 light-years from the center where gas compression and star formation are currently ongoing. This ring is one of Andromeda's more distinctive internal features. It is not a single arm, but a roughly circular structure of enhanced density encircling the galaxy's center at a moderate radius. Some interpretations suggest it was produced or emphasized by a past gravitational interaction, perhaps a smaller galaxy passing through the disk at some earlier time, sending a ring-shaped compression wave outward through the material, the way a stone dropped in water sends circular ripples to the edge. If this is the case, the ring is a slowly fading memory of a collision that ended long ago, its ripple still moving outward, still compressing gas and triggering new stars as it goes. The outer disk of Andromeda shows something else worth noting slowly. It is warped. The disk is not a perfect flat plane across its entire extent. The outer edges curve upward on one side and downward on the other, like a brim of a hat that has been slightly deformed. This warping is common in spiral galaxies and is generally thought to be caused by gravitational interactions, the pull of satellite galaxies, or the tidal influence of close companions, bending the outer parts of the disk over time. The stars in the outer disk of Andromeda are older, on average, than those in the inner regions. This is another general feature of spiral galaxies. The disk is not uniform in its stellar populations. The central bulge tends to contain old stars, formed long ago when the galaxy was young and dense. The outer disk contains a mix of old and younger stars, with star formation concentrated in the spiral arms and the dust-rich regions. The very outermost parts contain mostly old stars that have been slowly drifting outward over billions of years. The orbital speed of stars in Andromeda varies with distance from the center, but not in the way you might intuitively expect. Near the center, where most of the visible mass is concentrated, stars orbit relatively quickly. But in the outer regions, instead of slowing down, as you might expect from the declining influence of the central mass, the orbital speeds remain relatively high. This flat rotation curve is one of the observational signatures of dark matter. The mass that is keeping those outer stars moving quickly is not visible, not in the disk, not in the bulge. It is the unseen dark matter halo extending far beyond the bright disk. When you trace the motion of Andromeda's disk stars, you are therefore tracing the gravitational influence of something much larger than what you can see. The bright disk is embedded in a cloud of dark matter that outweighs it many times over, and every star in every orbit is feeling the pull of that invisible mass as much as the pull of all the visible stars combined. The galaxy is, in a sense, a thin, luminous coating on a much larger dark structure, a bright disk of stars and gas wrapped around an enormous dark sphere of matter we cannot directly observe. The timescales of orbital motion in Andromeda are, by any ordinary standard, enormously long. A star in the outer disk of Andromeda might take several 100 million years to complete a single orbit around the galaxy's center. In the time since complex animals first appeared on Earth, such a star would have completed only a handful of circuits. In the entire span of human recorded history, 10,000 years, at a generous estimate, the star would have moved through an orbital arc so small as to be unmeasurable by any current instrument. And yet the motion is real, constant, continuous. Every star in Andromeda is moving. The galaxy is rotating. The spiral arms are propagating slowly through the disk. Dust clouds are slowly collapsing to form new stars, and old stars are slowly dying and scattering their material back into the interstellar medium. All of this is happening continuously across a span of 100,000 light years, at timescales so long that from the outside it all appears perfectly still. The disk of Andromeda, seen in images, shows an illusion of solidity. It looks like something you could hold a flat, structured object with defined arms and a bright center and darker dust lanes. But it is not solid in any meaningful sense. The space between stars in the disk is enormous, incomprehensibly empty. If you were somehow transported to a random point in Andromeda's disk, you would see a sky full of stars, more stars than our own sky, because you would be in a denser region, but you would not feel crowded. The nearest star would still be light years away. The disk is filled with space, not matter, and the matter within it is separated by distances that make our solar system feel intimate by comparison. What gives the disk its appearance of solidity when viewed from outside is simply the combined light of hundreds of billions of stars, each one small and distant, blurring together at this scale into a smooth, continuous glow. The structure, the arms, the dust lanes, the bright ring emerges from slight variations in the density of stars and gas, variations that are real but subtle, differences of perhaps a few % in how many stars occupy a given region of space. It is a very gentle pattern, painted in very faint variations across an enormous canvas. Even its shape is not something the galaxy holds, but something it is continuously becoming, a form maintained by motion, by the ongoing dynamics of gravity and rotation and the slow cycling of matter through stars and back again into the diffuse medium between them. The spiral arms are not carved into the galaxy. They are a pattern that arises from the physics of how disks of gas and stars rotate, and they persist as long as the rotation continues and the disk has enough material to maintain the wave. At the center of Andromeda, there is a black hole. This is not unusual. Every large galaxy that has been carefully studied appears to contain a supermassive black hole at its center, an object of enormous mass compressed into a region much smaller than the stellar disk that surrounds it. These central black holes are not well understood in detail, but their presence is consistent and their influence on the surrounding galaxy is significant, particularly early in the galaxy's history, when they may have grown rapidly and radiated enormous amounts of energy. The black hole at the center of Andromeda is estimated to be roughly 100 million times the mass of the Sun. This is large compared to our own galaxy's central black hole, which is estimated at about 4 million solar masses. But it is not unusually large in the context of supermassive black holes in general. There are galaxies that contain black holes billions of times the mass of the Sun, objects so massive they strain credibility, detectable from across the observable universe by the energy released as they consume surrounding material. Andromeda's central black hole, by comparison, is a quiet and somewhat moderate example. It is also, notably, inactive. The most luminous objects in the universe, quasars and active galactic nuclei, are powered by supermassive black holes, actively consuming large amounts of gas and dust, releasing energy as infalling material heats up and radiates before crossing the point of no return. These objects shine with a luminosity that can outshine their entire host galaxy by factors of hundreds or thousands, and they are visible across enormous cosmic distances. Andromeda's central black hole is not doing this. It is, in the language of astronomy, a quiescent black hole, one that is not currently consuming material in large quantities and therefore not releasing large amounts of energy. It sits at the center of the galaxy, surrounded by stars, holding its enormous mass in a region of space no larger than the distance from the Sun to the nearest few stars, and it does very little that can be detected from the outside. It is present. It is massive. It exerts its gravitational influence on the orbits of stars around it. But it is not dramatic. There is something calming about this. The image of a black hole, in popular imagination, is often one of violence and consumption, a voracious dark mouth swallowing everything around it. But most supermassive black holes, for most of their existence, are not doing any of that. They grew during earlier epochs, when gas was more abundant and infall more common. Now, in the current era of the universe, most large galaxies are relatively gas-poor in their central regions, and their central black holes sit quietly, surrounded by old stars, disturbing nothing. The center of Andromeda is surrounded by a dense nuclear star cluster, a concentration of stars so compact and so numerous that the night sky, as seen from within that region, would be extraordinary. Not that any stars within it would be planets capable of supporting observation, but the thought experiment is worth following slowly. From deep within the nuclear star cluster, the sky would be filled with stars bright enough to rival our moon, stars so close together in apparent position that the sky would never fully darken. It would be a sky of almost perpetual stellar light, quiet, dense, and ancient, since most of these stars are very old. Andromeda's central region contains something distinctive and unusual, a double nucleus. When early, high-resolution observations of Andromeda's center were made, astronomers found not one but two concentrations of brightness in the nuclear region, separated by only a small distance. This double structure was puzzling, because there is only one central black hole, and simple models of galactic centers do not naturally produce two separate peaks of brightness. The explanation, when it was worked out, turned out to be a question of orbital geometry rather than a second separate structure. The double appearance of the nucleus arises from the distribution of stars in a ring-like orbit around the black hole. Most of the stars in this nuclear ring are concentrated toward one side of their orbit, the side farthest from the black hole, where orbital mechanics cause stars to spend more time and therefore appear denser. This creates one bright concentration. The black hole itself sits slightly offset from the geometric center of the ring, and the actual physical center creates a secondary concentration. Two brightness peaks, one object. This is a gentle reminder of how appearances can be misleading at galactic scales. What looks like two separate things may be one thing seen from an angle that creates the illusion of doubling. The center of Andromeda, for all its apparent complexity, resolves into a single black hole surrounded by stars following slightly eccentric orbits, the whole thing quiet, dense, and ancient, turning in the dark at the center of a trillion-star system. Within the nuclear region, there are also unexpectedly young stars, stars that appear to have formed relatively recently, in a region where new star formation seems difficult to sustain. Near a supermassive black hole, the tidal forces are extreme, and gas clouds that might otherwise collapse to form stars tend to be torn apart before they can. Yet young stars are present. How they form there is one of the genuinely open questions about galactic centers. Perhaps they migrated inward from the surrounding disk. Perhaps they formed in unusual conditions that allowed collapse despite the tidal environment. Perhaps the history of the nuclear region is more complex than current models suggest. The presence of these young stars adds a small note of uncertainty to the quiet center of Andromeda. It is not entirely inert. Something happened there, or is happening, that our current understanding does not fully account for. This is not troubling. It is simply the ongoing texture of real knowledge, which is always incomplete at the edges and always has soft places where understanding has not yet fully settled. Moving outward from the black hole, through the nuclear star cluster, through the central bulge, the density of stars decreases slowly. The bulge of Andromeda is a rounded, roughly spherical concentration of old stars surrounding the central disk, a feature common to spiral galaxies, thought to have formed early in the galaxy's history when the first burst of star formation was most intense. The stars in the bulge are old, red, and dim by the standards of young stars, and they orbit the center in elongated loops rather than the more orderly, circular orbits of disk stars. The bulge contributes significantly to the overall brightness of Andromeda as seen from Earth. When you look at the faint oval of light in the night sky, much of what you are seeing is the bulge, the concentrated core of the galaxy that stands out even at this distance because it is so dense in stars. The disk extending outward from the bulge is dimmer and larger, and it fades gradually into the surrounding dark. The gravity at the center of a galaxy like Andromeda is not chaotic or violent in any meaningful sense. It is simply strong, consistently, enormously, reliably strong, and every star in the nuclear region has settled into an orbit calibrated to that strength. The stars near the center move faster than those further out, completing their shorter, tighter orbits more quickly, and the whole nuclear region hums along in its own dense rhythm, distinct from the slower turning of the outer disk. At the very center of this system, the black hole sits in a kind of gravitational stillness. Not the stillness of nothing happening, but the stillness of a system in balance mass, held against the expansion of the universe by its own gravity, stars held in their orbits by the combined pull of everything, the black hole itself, neither consuming nor releasing, simply present, simply massive, simply holding the center while the rest of the galaxy turns around it. At the center, motion does not disappear. It simply stops feeling like motion at all. Step back now, very slowly, and let the bright disk of Andromeda shrink in the frame. The spiral arms, the dust lanes, the bright central bulge, let all of that recede until the galaxy becomes a smaller shape in the center of a much larger context. Because Andromeda does not end at its visible disk, the galaxy extends outward into a vast and diffuse structure, a halo of stars, gas, and dark matter that reaches enormous distances in all directions, far beyond anything visible in ordinary photographs. The galactic halo is not a bright structure. It is made of old stars, stars so ancient they formed before the disk had settled into its current form, stars that orbit the galaxy in wide, elongated, looping paths that carry them far above and below the disk plane before swinging them back inward. These halo stars are diffuse and dim, spread across a much larger volume than the disk, and their combined light is so faint that it took careful observations with sensitive instruments to detect them at all. Scattered through this halo are globular clusters, dense, spherical collections of very old stars, tightly gravitationally bound, orbiting the galaxy as a whole, the way satellites orbit a planet. Globular clusters are among the oldest structures in the universe. The stars within them formed early in cosmic history, more than 10 billion years ago in many cases, and they have been traveling together ever since in their slow, wide orbits around the host galaxy. Andromeda has hundreds of known globular clusters, more than any other galaxy in the local group. They come in a range of sizes, from compact systems with hundreds of thousands of stars to extended ones with millions, and they orbit at all distances from the galaxy center, some close in, and some in wide orbits that carry them far into the halo. Studying these clusters gives astronomers a way to probe the history and mass distribution of Andromeda without being able to resolve the underlying dark matter. Directly, the orbits of the clusters trace the gravitational potential of the whole system. Some of Andromeda's globular clusters are thought to be the stripped cores of dwarf galaxies, small galaxies that fell into Andromeda's gravitational influence long ago and were slowly torn apart as they spiraled. Inward, their outer stars stripped away and scattered into the halo, while the dense central region survived as what now appears to be a compact star cluster. This process, called tidal stripping, is one of the mechanisms by which large galaxies grow over time, incorporating smaller ones, absorbing their material, gradually building up mass. The evidence of this process is visible in Andromeda's halo. Detailed surveys of the faint stellar populations in the halo have revealed stellar streams, long, thin arcs of stars, stretching across enormous distances, the remnants of dwarf galaxies that were disrupted and dispersed by tidal forces as they fell toward Andromeda. These streams are the ghost traces of former companions, their stars now scattered along the path their parent galaxy once traveled, moving through the halo in a slow dispersal that will continue for billions of years before the streams fade completely into the background. One of the most prominent of these features is a large stellar structure in Andromeda's halo, sometimes called the Giant Stellar Stream, a broad arc of stars thought to be the remnants of a dwarf galaxy that made a close pass at Andromeda in the relatively recent cosmic past and was largely consumed in the encounter. The stream contains millions of stars, spread across tens of thousands of light years, following the orbital path of the long-departed dwarf. It is a kind of fossil record, written in stars instead of stone, of a gravitational encounter that ended billions of years ago. Andromeda continues to have satellite galaxies in orbit, around its smaller companions that have not yet been absorbed, that continue to orbit at various distances. Some of these are large enough to be visible in telescopes as distinct galaxies. Others are tiny, containing only millions of stars, and are known only from careful surveys of the halo region. Each one is, in a sense, a future merger, a small galaxy gradually losing orbital energy to the tidal forces of the larger system, likely to be incorporated over billions of years. The hot gas halo of Andromeda is another component that extends well beyond the visible disk. This is a diffuse atmosphere of extremely hot, ionized gas surrounding the galaxy, not the cold molecular gas of the disk that forms stars, but a tenuous, high-temperature medium that emits in X-ray wavelengths and extends far into the intergalactic region. This hot gas is in part the product of supernova explosions and stellar winds over billions of years, material heated to extreme temperatures by stellar death events and launched outward from the disk into the surrounding space, where it accumulates as a diffuse, hot corona around the galaxy. The hot gas halo of Andromeda is thought to extend perhaps 300,000 light-years or more in all directions, 3 times the diameter of the visible disk. Within this enormous volume, the density is extremely low, but the gas is present, and its gravitational interaction with infalling material and orbiting satellites is real and ongoing. When dwarf galaxies fall into Andromeda's gravitational influence, they pass through this hot gas halo, which can strip away their own cold gas, quenching their ability to form new stars. Beyond the hot gas halo is the dark matter halo, which extends even further, perhaps 1 million light-years or more in radius, containing the majority of the galaxy's total mass in a form we cannot see. This invisible sphere of matter is what allows the galaxy to hold its shape, what keeps the satellite galaxies in their orbits at large distances, what determines the eventual fate of any material that falls toward the system from the intergalactic medium. The dark matter halos of the Milky Way and Andromeda are, at this scale, not far apart. They extend outward until they nearly touch. The boundary between the two systems is not sharp, it is a gradual transition, a region of space where both halos overlap slightly, where material is gravitationally influenced by both great galaxies simultaneously. In this sense, the two galaxies are already, in the most diffuse and invisible way, overlapping. There is a particular quality to the outer halo that deserves a moment of quiet attention. It is the oldest part of the galaxy in terms of stellar populations. The halo stars formed first, when the universe was young and the proto-galactic cloud of gas was just beginning to collapse and form stars. Before the disk had settled, before the spiral arms had appeared, there was a first generation of star formation in the collapsing cloud, and some of those stars are still present, still orbiting, in the halo of Andromeda today. They are the galaxy's memory of its own beginning, traveling slowly in their wide orbits, carrying chemical signatures of a time when the universe had yet to make most of the heavier elements. The stellar streams are a different kind of memory, not of the galaxy's own formation, but of the encounters it has had since then. Each stream is a record of a specific event, a dwarf galaxy arriving, a tidal encounter, a slow destruction and absorption. The halo is a palimpsest, a surface written on many times, each layer faintly visible beneath the next. The galaxy's history is not stored anywhere in text or image. It is written in the positions and motions and chemical compositions of millions of stars spread across hundreds of thousands of light-years. Beyond the visible galaxy, there is still structure, but it is made of memory rather than light old stars following ancient paths, streams of dispersed companions, invisible mass, shaping everything from outside the frame of what can be seen. Every observation of Andromeda is an observation of the past. This is true of all astronomical observation. The light we receive from any distant object left that object some time ago, and what we see is not the object as it is now, but the object as it was when the light departed. For nearby objects, this time delay is negligible. The Moon is about 1¼ light seconds away, so we see it as it was slightly more than a second ago. The Sun is 8 light minutes away. But for Andromeda, the delay is 2.5 million years. Every photograph of Andromeda is a portrait of the galaxy as it existed 2.5 million years ago. The stars visible in those photographs may have changed since then. Some may have exploded, some may have been born. The spiral arms may have shifted slightly in their patterns. We have no way of knowing what Andromeda looks like right now in any cosmic present tense sense. We only know what it looked like when the light we are currently receiving was emitted. In some ways, this is simply a constraint, a limitation of the fact that information can travel no faster than light. But there is another way to hold this. Every photon arriving from Andromeda tonight has been travelling since before our species existed. It was emitted by a star in a galaxy 2.5 million light-years away during the geological epoch, when early hominids were walking on an African savanna without any idea that the faint smudge above them was a galaxy at all. And that photon has travelled continuously, without stopping, through entirely empty space, for all the time since, through the rise and fall of every human civilization, through every moment of history, until tonight, when it arrives and lands on a detector, or in a retina, or in the mind of someone lying still and listening to the night. Astronomers observe Andromeda across many different wavelengths of light, and each wavelength reveals a different component of the galaxy's structure. Optical light, the range our eyes are sensitive to, shows the stars most directly, particularly old red stars and bright young blue ones. Infrared light penetrates dust and reveals the warm emission from heated grains, tracing spiral structure and star-forming regions that are hidden from optical view. Ultraviolet light reveals the hottest, youngest stars, the ones burning most intensely and most briefly. Radio waves trace the distribution of cold hydrogen gas across the disk and halo. X-ray observations detect extremely hot gas and compact remnants of stellar deaths, neutron stars, and stellar mass black holes. By combining these different wavelength observations, astronomers build a layered understanding of the galaxy that no single image can contain. The galaxy is not one thing, it is many overlapping systems, each visible in its own wavelength range, each telling a different part of the structural story. The cold gas of the disk, the hot gas of the halo, the young stars of the arms, the old stars of the bulge and halo, the compact remnants of stellar death, all of these coexist in the same volume of space, each invisible to the others, each detectable only in a narrow range of the electromagnetic spectrum. The distance to Andromeda was established using a specific type of pulsating star called a Cepheid variable. These stars have a reliable relationship between their pulsation period and their true luminosity. The longer the period, the more luminous the star. By measuring how long a Cepheid takes to complete one cycle of brightening and dimming, astronomers can calculate how bright it truly is. Comparing that to how bright it appears allows them to calculate the distance. This method, first applied to Andromeda in the early 20th century, gave the first reliable estimate of the galaxy's distance and demonstrated definitively that it lay far outside the Milky Way. Cepheid variables are still used as distance indicators today, and their application to Andromeda has been refined many times since the first measurements. Each refinement has adjusted the distance estimate somewhat, settling over the decades toward the currently accepted value of approximately 2.5 million light-years, with uncertainties that are now quite small relative to the total distance. Andromeda is the best measured distant galaxy in terms of distance accuracy because its proximity allows individual stars, including Cepheids, to be resolved and studied. The study of Andromeda has, over the past century, continuously informed our understanding of the Milky Way. Because we live inside the Milky Way, our view of its own structure is necessarily limited and complex. We cannot see the full shape of our own galaxy from within it, and our position in the disk means that many features are hidden behind dust. Andromeda, seen from outside, gives astronomers a template for a spiral galaxy of similar size and structure, and the things learned from studying Andromeda can be applied, with appropriate adjustments, to understanding what our own galaxy probably looks like from a distance. Andromeda is, in this sense, a mirror of sorts, not a perfect one, not an identical twin, but a kindred structure that illuminates the general principles of how a large spiral galaxy is organized. When astronomers learn something new about the structure of Andromeda's halo, or the dynamics of its spiral arms, or the history of its satellite interactions, the same processes likely apply to the Milky Way, and the knowledge gained from the neighbor enriches the understanding of home. The relationship between observation and time in astronomy takes on a particular quality when considering Andromeda. Most distant astronomical objects are so far away that we cannot study their evolution in any meaningful sense. A galaxy billions of light-years away appears the same in any human observation period, and its present state is so far removed in time from what we can see that the two might as well be different objects. Andromeda is close enough that we can, in principle, detect changes over decades of careful observation, the proper motions of individual stars, the precise orbits of satellite galaxies, the slow drift of the galaxy itself across the sky. These changes are vanishingly small, far below the threshold of naked eye perception, but they are there and they are being measured. The motion of Andromeda through space, its slow drift toward the Milky Way, complicated by its sideways motion across our line of sight, is being tracked with increasing precision. The result of decades of observation is a slowly emerging picture of the galaxy's true three-dimensional motion, not just its speed of approach, but the full arc of its path. Every image of Andromeda is not a place, but a slow arrival of ancient light photons that have crossed more than 2 million light-years of space, carrying information about a galaxy as it was before humans existed, landing in our instruments and our eyes, and becoming, slowly, knowledge. Andromeda and the Milky Way are moving toward each other. This is a fact, and it has been known for over a century, and it is, in the scope of what it means for anything, entirely gentle. The approach is slow by any measure that matters to a human life, or to a civilization, or to a species. In 100 years, the two galaxies will be approximately the same distance apart as they are tonight, to within a margin far smaller than the diameter of the local stellar neighborhood. The approach is real, measurable, ongoing, but it is measured in billions of years, not centuries, and its immediate consequences for anything you can see or touch or hold are, for now, exactly zero. Andromeda is approaching the Milky Way at roughly 110 kilometers per second. This sounds fast. It is fast, by any standard of terrestrial motion. But the distance between the two galaxies is 2.5 million light-years, and at 110 kilometers per second, it would take approximately 45 times longer than the current age of the universe to cover that distance, except that the galaxies are already approaching, already much closer than they began, already in the final few billion years of their long approach. The most careful measurements of Andromeda's motion suggest that the two galaxies will experience their first close encounter in approximately 4.5 billion years. This is longer than the current age of the Earth. It is comparable to the remaining lifespan of the Sun as a stable star. It is an immense span of time in which essentially anything could happen, and in which the word soon has no meaning whatsoever. What will happen when the two galaxies interact is not entirely certain, because the trajectory of the encounter depends on the precise sideways component of Andromeda's motion, the part that is not directly toward us but perpendicular to our line of sight, and this component is harder to measure than the approach speed. Current estimates suggest the galaxies will indeed collide and merge rather than passing by each other, but the exact geometry and timing of the interaction have some uncertainty built in. Galaxy mergers are not collisions in the ordinary sense. When we speak of two solid objects colliding, we mean two things hitting each other and transferring energy through direct physical contact. Galaxies cannot do this because they are not solid. The stars within a galaxy are so widely spaced that even when two galaxies pass through each other, the probability of any two individual stars actually colliding is extremely small. The galaxies can interpenetrate without their stars physically striking one another. What does happen is gravitational. As the two galaxies approach, the gravity of each one distorts the shape of the other. Stars are pulled out of their orbits by the tidal forces of the passing mass. Long streamers of stars are drawn out from both galaxies and scattered into the intergalactic space. Gas clouds are compressed by the encounter, triggering bursts of new star formation as the compressed material collapses. The two central black holes are eventually drawn toward each other by the loss of orbital energy, spiraling inward over millions of years before finally merging. The first encounter, which will bring the two galaxy disks near each other, will not immediately produce a merged galaxy. It will produce a gravitationally disturbed system, both galaxies stretched and deformed, trailing stellar streams, with a brief burst of star formation from the compressed gas before they separate again and begin a second approach. This back-and-forth pattern, close passage, separation, reapproach, may repeat several times before the two systems finally merge into a single structure. The eventual outcome is expected to be a single galaxy of a type called an elliptical galaxy, a roughly spherical or oblate distribution of stars, lacking the organized disk and spiral arms of either parent galaxy, with a much lower rate of ongoing star formation because the gas has been consumed or dispersed in the merger process. This future merged galaxy has sometimes been called Andromeda, a name that is not officially used in astronomy, but that captures the imaginative reality well enough. The Sun will still exist during the early stages of this merger, though it will be an older star by then, and the Earth will long since have become uninhabitable. The Sun's position in the disk of the Milky Way will shift as the merger proceeds. The Sun may end up in a very different location relative to the new galaxy's center. But the probability of the Sun encountering another star directly is extremely low because, as noted, stellar collisions in galaxy mergers are rare. The Sun will simply drift into a new orbit in the new merged system, along with every other star that survives the gravitational reorganization. The merger is not something to feel urgency about, because there is no urgency in it. It is a slow gravitational process, playing out on timescales entirely beyond human relevance. It is happening, in a sense, right now. The approach continues. The mutual gravitational influence is real and present, but its perceptible consequences will not arrive for billions of years. There is something almost beautiful in the patience of it. Two great spiral galaxies, each containing hundreds of billions of stars, slowly drawn together by the accumulated gravity of all their mass and all their dark matter halos, over a span of time that dwarfs the age of the Earth. The interaction has been going on since the local group formed, since the mutual gravity of the two systems began to dominate over the general expansion of space. It will conclude, in its own slow way, when the two become one, a quieter, rounder, more settled galaxy, old and large, and no longer forming many new stars. Even the merger of the two central black holes, one currently 4 million solar masses, the other roughly 100 million solar masses, will be a quiet process on the timescale of the universe. Black hole mergers are energetic events in terms of gravitational wave emission, but they take place at the center of the galaxy over millions of years, and the waves they emit carry energy away from the system slowly and invisibly. Nothing is arriving quickly. Nothing is leaving. Only distance, changing its shape, two galaxies that were once separated by intergalactic emptiness, slowly becoming one system, one family of stars, one quiet elliptical remnant of two spirals that once were neighbors. Andromeda has been a subject of human observation for as long as there have been humans, with clear, dark skies and the inclination to look upward and wonder. The records of it in historical, astronomical texts are numerous, it appears, in Persian star catalogues from more than 1,000 years ago, described as a small cloudy patch near a chain of stars, noted and catalogued without the context to understand what it was. Every observer who noted it added a small entry to a long record of human noticing, a catalogue of attention paid across centuries to a faint and patient light. The question of what it was, cloud, gas, or something else, entirely occupied astronomers for centuries without resolution. The instruments available were not sufficient to settle the debate, and the theoretical framework was incomplete. The Milky Way was known to be a vast system of stars, but whether it was all there was, whether the universe extended beyond its edges, was genuinely uncertain. The nebulae Andromeda among them could be inside or outside, and the evidence pointed in contradictory directions depending on which observations you emphasized. The resolution of this debate in the early 20th century is a case study in how science works at its best, not through sudden revelation, but through the slow accumulation of better data, better instruments, and eventually, an observation clear enough to settle the question. The identification of Cepheid variable stars in Andromeda's outer regions, and the calculation of their distance, did not merely answer the question of Andromeda's nature. It expanded the known universe enormously, and it did so not with drama, but with quiet precision, a series of measurements, a calculation, a number that changed everything. Since that expansion of the frame, Andromeda has been observed with every instrument and technique available to astronomy. Each new generation of telescopes has added detail and depth to the portrait. Radio observations revealed the distribution of hydrogen gas across the disk and halo. Infrared surveys exposed the dust structure and star-forming ring. Ultraviolet observations catalogued the young, hot star clusters scattered through the arms. X-ray observations found the compact remnants of stellar deaths and the diffuse hot gas of the halo. Gravitational lensing studies have probed the dark matter distribution. The result is the most detailed and complete portrait of any galaxy outside the Milky Way, a multi-layered, multi-wavelength study that has been building for a century and continues to improve with every new instrument. Each new observation adds a layer, fills in a blank, or reveals a previously unseen structure. The faint stellar streams in the halo, for example, were not known until sensitive wide-field surveys were conducted in the past few decades. The precise orbital motion of Andromeda was not known until recent measurements with space-based telescopes achieved the necessary precision. What all of this observation tells us is that Andromeda is a deeply ordinary galaxy in the most respectful sense of that word. It is a large spiral galaxy following the patterns common to this class of objects: a spiral disk, a central bulge, a supermassive black hole, globular clusters, satellite galaxies, a dark matter halo. Every feature it shows has been seen in other galaxies in various forms and degrees. It is not exotic or unusual. It is a well-represented example of the type of galaxy that constitutes the backbone of the observable universe. And yet, because of its proximity, because of the extraordinary detail with which it can be studied, Andromeda has served as the reference case, the standard against which other galaxies are compared, the example to which astronomers return when they want to know what a large spiral galaxy looks like in full detail. It has shaped our understanding of spiral structure, galactic dynamics, halo formation, satellite interactions, and dark matter distribution more than any other galaxy outside our own. The sky continues to carry Andromeda tonight, exactly as it has on every clear night in human history, unchanged to human perception. The faint smudge is the same faint smudge it was 10,000 years ago and 100,000 years ago. It will be the same faint smudge tomorrow night. No individual human life is long enough to see it change in any observable way, and no human civilization has been long enough to document a change. It simply persists, turning slowly, sending its light continuously outward in all directions, some of it always heading toward us. There is a particular kind of constancy in that, and a particular kind of comfort. In a world where most things change, where cities rise and fall, where species come and go, where the surface of the planet shifts over geological time, Andromeda is steady. It is not going anywhere on any timescale that matters to us. It is not doing anything dramatic or sudden. It is simply there, faint and immense and patient, the way the night itself is patient, the way sleep is patient, waiting for the mind to let go of the day and fall into it. The spiral arms of Andromeda deserve a longer moment of attention because they are among the most visually striking features of the galaxy, and because their nature is genuinely interesting in ways that are easy to overlook in favor of more dramatic topics. As noted earlier, spiral arms are density waves, not fixed structures, but slowly propagating patterns of slightly increased density in the disk material. This picture was developed theoretically in the second half of the 20th century and has been confirmed by detailed observations of many spiral galaxies. It resolved a long-standing puzzle about why spiral arms exist at all, since simple models of rotating disks predicted that differential rotation would wind any fixed arm into an ever tighter coil until it disappeared. The density wave model explains why arms persist over billions of years. The wave is self-maintaining. Compressed gas in the arm forms new stars, and those stars, particularly the most massive and luminous ones, illuminate the arm and make it visible. The massive stars live short lives and die explosively, sending shock waves back into the surrounding gas that can trigger further compression and further star formation. The arm is, in a sense, a slowly moving zone of enhanced star birth and death, traveling around the disk at its own characteristic speed, somewhat different from the orbital speed of the stars and gas within the disk. The arms of Andromeda are not perfectly regular. They show asymmetries and irregularities that suggest the influence of past interactions with satellite galaxies, with the gravitational tidal field of the larger system, with internal dynamical instabilities in the disk itself. The outer disk shows the warp already mentioned, and the inner regions show the dust ring that may be a ripple from a past penetration event. These irregularities are normal and expected. A real galaxy, with a history of gravitational encounters and ongoing internal dynamics, will not show the idealized symmetry of a textbook spiral. The star-forming ring, which stands out clearly in infrared observations of Andromeda, is thought to be a particularly active zone where conditions for star formation are currently enhanced. Within this ring, giant molecular clouds, the cold, dense aggregations of gas from which stars form, are collapsing at a modest but steady rate, producing new stars ranging from small and dim red dwarfs to large and briefly brilliant blue giants. The blue giants live only a few million years before dying in supernova explosions, while the red dwarfs will survive for tens of billions of years. The ring currently lights up in the characteristic colors of mixed stellar populations, older red light from stars born previously, and younger blue light from the most recently formed. The concept of star formation happening at a rate is worth sitting with for a moment. Andromeda forms new stars at a modest pace. Astronomers estimate it at somewhere between a fraction of a solar mass to a few solar masses per year, meaning that in a given year, the galaxy produces new stellar material equivalent to, at most, a few suns. This is not a high rate for a galaxy of its size. Many star-forming galaxies in the universe, particularly those in mergers or with abundant gas supply, form stars far more rapidly. Andromeda is in a relatively quiet phase of its evolution, past the peak of its star-forming activity, gradually consuming its remaining supply of cool gas at a slow and sustainable pace. The dust lanes visible in optical images of Andromeda are not uniform. They vary in thickness and darkness, reflecting the clumpy distribution of cold molecular material in the disk. Some regions have particularly dense concentrations of dust-enshrouded gas, nearly opaque to optical light, and these are among the most active sites of current star formation, hidden from view, in visible light, but bright in infrared and radio observations. New stars form within these cocoons of dust, heating it from inside, until the most energetic stars eventually dissipate the surrounding gas and become visible as part of a young star cluster. Young star clusters in Andromeda are distributed throughout the disk, concentrated in the spiral arms and the star-forming ring. They range from small associations of a few dozen stars to large clusters of hundreds of thousands, spanning a wide range of ages. The youngest are still embedded in gas and dust, barely weeks or months old in stellar terms. The older ones have dispersed their birth material and are now drifting through the disk as compact groups, gradually dissolving into the general stellar population over hundreds of millions of years as tidal forces pull them apart. The comparison with the Milky Way's star-forming regions is instructive. The Orion Nebula, visible to the naked eye as the fuzzy middle star in Orion's sword, is a star-forming region in the Milky Way, a relatively modest example, producing a few hundred new stars in a region about 40 light-years across. Andromeda contains many such regions, and larger ones distributed throughout its disk. They are too distant to be seen individually without a telescope, but in aggregate they contribute to the faint blue tinge of the disk's outer regions visible in careful photographs. The interstellar medium of Andromeda, the gas and dust between the stars, is not uniform either. It is a complex, multi-phase medium with regions of very different temperature and density coexisting in approximate pressure balance. The cold molecular gas of the star-forming clouds exists alongside warm atomic gas, and both are surrounded by and embedded in a hotter, more diffuse ionized component. Each phase has its own characteristic emission or absorption signature, detectable in different parts of the radio and optical spectrum. This multi-phase structure is not unique to Andromeda. It is a general feature of the interstellar medium in all disk galaxies, but it means that the disk is far more complex than any simple description captures. The spiral arms are not purely uniform dense zones. They are regions where the multi-phase medium is somewhat more compressed on average, where the cold gas fraction is slightly higher, where the probability of molecular cloud formation and subsequent star formation is elevated. The detail is always more complicated than the summary, and the summary is always more complicated than the image. One of the more quietly remarkable things about Andromeda, considered as a whole, is simply how long it has existed. The galaxy formed early in the history of the universe. Its oldest stars are more than 10 billion years old, and the first burst of significant star formation likely occurred within the first few billion years after the Big Bang. This means Andromeda has been a galaxy, a rotating system of stars, gas, and dark matter for longer than the Earth has existed, longer than the Sun has burned, longer than the solar system has been anything more than a diffuse cloud of gas around a protostellar condensation. The processes that maintain the galaxy have been ongoing for all of that time. Stars have been forming and dying continuously in the disk for more than 10 billion years. The globular clusters orbiting in the halo have been making their slow circuits for nearly as long. The dark matter halo has persisted, invisible and stable, providing the gravitational framework within which everything else has evolved. The spiral structure has come and gone and reformed many times, driven by density waves that propagate through the disk on timescales of hundreds of millions of years. In the context of all this time, the period during which humans have been observing Andromeda is extraordinarily brief. A few thousand years of naked eye observation, a few hundred years of telescopic study, and a century of modern multi-wavelength astronomy. These together constitute an infinitesimally small fraction of the galaxy's lifespan. We have caught the galaxy in a single, extremely brief snapshot of its long evolution. This snapshot is rich in detail and has told us an enormous amount, but it is worth remembering that we are seeing a galaxy that has been doing what it does for billions of years before we were watching, and will continue doing it for billions of years after our instruments fall silent. The star formation ongoing now in the dust ring has predecessors going back to the galaxy's formation. The stellar streams in the halo are not the first such streams. Earlier mergers produced earlier streams that have long since dissolved into the background stellar halo, their constituent stars now indistinguishable from any other old halo star. The galactic halo, as a repository of the galaxy's gravitational history, contains stars of many different origins. Some formed in the very first burst of star formation when the proto-galactic cloud collapsed. Some migrated outward from the disk over long timescales, pushed by various dynamical mechanisms. Some arrived as members of disrupted satellite galaxies and now orbit as free stars in the halo population. The halo is a mixture of all these histories, and separating them requires careful analysis of the chemical compositions and orbital properties of individual halo stars, a field of research still actively developing. Every star in Andromeda's halo is, in a sense, a traveller. None of them has stayed in one place. They have been orbiting for billions of years, their paths shaped by the changing gravitational field of the galaxy as it has grown and evolved. The galaxy itself has changed. Mergers have added mass. Tidal interactions have redistributed orbits. the dark matter halo has gradually grown through accretion. The halo stars have been passengers in this evolution, their orbits slowly adjusting to the changing gravitational environment, sometimes disrupted by passing mass concentrations, generally following the slow drift of dynamical relaxation. And yet, despite all this change, the galaxy looks broadly similar today to what it would have looked like several billion years ago. Spiral galaxies are stable structures. In a general sense, the overall form is maintained by the physics of rotation and self-gravity, and while individual features come and go, the general character of a large spiral persists over enormous timescales. Andromeda today is recognizably a galaxy of the same type as it was billions of years ago, even if the details of its arms, its satellite population, and its star-forming activity have all changed. This persistence is itself a form of stability, not the stability of an unchanging object, but the stability of a process that maintains its character over time, the way a river is always the same river, even though the water within it is always different. Andromeda is the pattern, and the stars within it are the water, and the pattern has been recognizable for a very long time. A galaxy is not just stars. The stars are perhaps the most visible component, the brightest and most immediately striking feature of any galaxy image, but they represent only a fraction of the galaxy's baryonic material, the ordinary matter that interacts with light. Equally important, and in many ways more fundamental to the galaxy's ongoing evolution, is the interstellar gas and dust that fills the spaces between stars. In Andromeda, the distribution of cold, neutral hydrogen gas has been mapped in detail using radio telescopes sensitive to the characteristic 21 centimeter radio emission that hydrogen atoms produce when the spin state of their electrons changes. This emission, invisible to optical instruments, passes freely through dust and reveals the full extent of the gas disk, including regions of the outer disk where the star density is too low to be easily visible in optical light. The cold gas disk of Andromeda is warped, as mentioned earlier, and it extends slightly further than the stellar disk. At large radii, the gas becomes very sparse, and the star formation essentially stops, not because the conditions for collapse are impossible, but because the gas is so thin that the probability of a cloud dense enough to form stars is extremely low. The outer regions of the disk are, in a sense, gas desert not empty, but too sparse to sustain the process that makes new stars. The chemical composition of the interstellar gas in Andromeda tells a story of stellar evolution. The universe began with almost no elements heavier than helium, hydrogen, and helium together, making up virtually all the matter produced in the Big Bang. Every heavier element that exists, carbon, oxygen, nitrogen, iron, silicon, everything else was produced inside stars. When stars die, they scatter this enriched material back into the interstellar medium, increasing the abundance of heavy elements available for the next generation of stars. Andromeda's interstellar medium has been enriched over billions of years by the deaths of countless stellar generations. The oldest stars in the galaxy, formed from nearly pristine hydrogen and helium, contain almost no heavy elements. The youngest stars, formed from material that has been processed through many earlier stellar generations, contain much higher abundances of elements like iron, carbon, and oxygen. This chemical gradient, older stars with lower metallicity, younger stars with higher metallicity, is a fingerprint of the galaxy's stellar evolution history, readable in the spectra of individual stars and of the integrated light of stellar populations. The chemistry of stars connects Andromeda to the rest of the universe in an intimate way. The carbon in the interstellar medium of Andromeda, the oxygen, the calcium and iron, all of it was processed through stellar interiors, fused from lighter elements by the thermonuclear processes that power stars, scattered by stellar winds and supernova explosions, mixed into the interstellar medium and incorporated into the next generation of stars and any planets that formed around them. This cycle of stellar birth, life, death, and chemical enrichment is one of the most important processes in galaxy evolution. The interstellar medium of a galaxy is not fixed, it is continuously being processed, enriched, and recycled. The gas that forms new stars today is chemically different from the gas that formed the oldest surviving stars, and the gas that will form stars a billion years from now will be different again, enriched by the deaths of the stars being born today. Andromeda's star-forming ring, discussed earlier, is a site where this cycle is particularly active. Gas is collapsing to form stars. Those stars are enriching the surrounding medium with their stellar winds and eventually their deaths, and the next generation of stars forms from slightly more chemically enriched gas. The ring is not just a region of new stars, it is a site of ongoing chemical evolution, a place where the galaxy is continuously reprocessing its own material. The satellite galaxies of Andromeda deserve a more careful look because they constitute a significant part of the extended Andromeda system, and because their study has revealed important information about galaxy formation and the behavior of dark matter on small scales. The two largest and most prominent satellite galaxies are known as M32 and NGC 205. Both are visible in modest telescopes, close enough to the main disk of Andromeda that wide-field photographs of the galaxy often capture all three objects in the same frame. The Great Spiral, with its two small companions nearby, like a planet with moons, though the scales involved make any such comparison collapse immediately under scrutiny. M32 is a compact elliptical galaxy unusually dense and small for its class, orbiting relatively close to Andromeda. It contains old stars and very little gas, suggesting it has long since exhausted or lost its star-forming material, most likely through tidal stripping as it has orbited Andromeda repeatedly over billions of years. Each pass through the denser regions of the host galaxy's gravitational field pulls a little more loosely bound material away, and over sufficient time, the galaxy is left with only what gravity can hold most tightly, its dense stellar core, old and red and quiet. NGC 205 tells a somewhat different story. It is a more diffuse elliptical galaxy, sitting a little further from Andromeda's center, and it shows traces of something unexpected in an elliptical, low-level star formation, faint evidence that new stars are still being made in small quantities. This suggests a relatively recent interaction with Andromeda, a close passage that compressed some of NGC 205's remaining gas, just enough to trigger the slow ignition of new stars. Its shape is slightly elongated and distorted, pulled by the same tidal forces that will eventually, over timescales long enough to be nearly meaningless, reshape it further. For now, it hangs in the sky near Andromeda, close enough to study in detail, its slow distortion a record of the gravitational conversation it is having with its host. Below these two large companions is a population of smaller dwarf satellite galaxies orbiting Andromeda at various distances. They are numerous, and many of them were entirely unknown until recently, so faint that only the sensitive wide-field surveys of the last few decades have been able to find them. They range from dwarf spheroidal galaxies, which are small and diffuse and old, containing little gas and no ongoing star formation, down to the smallest known galaxies, objects containing only a few million stars, glowing so faintly that they verge on invisibility against the background of the sky. The word galaxy, applied to these objects, requires a moment of adjustment. We are accustomed to thinking of galaxies as enormous structures. The Milky Way contains several 100 billion stars. Andromeda contains more. The smallest dwarf satellites of Andromeda contain a few million. They are galaxies in the sense that they are gravitationally bound stellar systems embedded in dark matter halos, but they sit at the far end of the scale from the grand spirals that anchor the imagination. They are, in a sense, the most primitive galactic structures, small dark matter halos that acquired just enough gas early in cosmic history to form a small population of stars, and then never grew further, frozen in that state by the combined effects of their low mass, the early cosmic radiation field, and the tidal influence of the host galaxy. That freezing is worth dwelling on. In the early universe, shortly after the first stars formed, the radiation they produced was energetic enough to ionize gas throughout the cosmos, to strip electrons from hydrogen atoms, and leave the intergalactic medium too hot to fall easily into small gravitational wells. Large dark matter halos, with deep enough gravitational potential, could hold their gas and continue forming stars. Small halos could not. The gas was heated away, or simply never accumulated, and the small halos were left with whatever stars they had already made, and nothing more. The dwarf satellites of Andromeda are, in part, fossils of this early epoch objects that reached a certain stage of development when the universe was young, were interrupted by physics operating at cosmic scales, and have changed very little since. They carry in their stellar populations a record of conditions in the early universe. Their stars are old and metal-poor, formed before many generations of supernovae had enriched the interstellar medium with heavier elements. They are, if you look at them the right way, windows into the first billion years of cosmic history. The satellite systems of the Milky Way and Andromeda have been studied and compared extensively because the number and distribution of dwarf satellites around a large galaxy is predicted by models of structure formation based on dark matter. The predictions initially seemed to fail badly. Early models predicted far more small satellites than were observed, not a small discrepancy, but an order of magnitude, a factor of 10 or more. This was called the missing satellites problem, and it generated considerable unease about whether dark matter models of structure formation were correct in their details. The problem has since been partially resolved on two fronts. Sensitive observational surveys have discovered many more faint dwarfs than were previously known, closing some of the gap between prediction and observation. And theoretical refinements have improved the models, accounting for the suppression of star formation in very small dark matter halos by the early cosmic radiation field, producing halos that exist but are essentially invisible because they never formed enough stars to be seen. The missing satellites in this picture are not missing. They are dark. They have halos but no light, small gravitational structures that acquired almost nothing in the way of stars and have been orbiting their host galaxy ever since in near total darkness. Some of the dwarf satellites that do have stars are not in stable long-term orbits around Andromeda. They are falling in recent arrivals in the gravitational influence of the large galaxy, captured from the outer reaches of the local group or from intergalactic space, pulled gradually inward by a gravity they cannot escape. As they fall, tidal forces begin to work on them. The gravity of Andromeda pulls more strongly on the near side of a dwarf galaxy than the far side, and this differential force distorts the shape of the smaller galaxy, stretching it slightly along the direction of the pull. Stars at the outer edges, held least tightly by the dwarf's own gravity, begin to be stripped away, pulled into long tidal tails that lead and trail the infalling galaxy in its orbit. Over time, over many orbits, each one bringing the dwarf closer to the center, each one stripping a little more material, the small galaxy comes apart. Its stars are scattered into a long arc, a stellar stream following the orbit that the galaxy once traced, a ghostly record of something that was once a coherent system and is now dispersed. The stellar streams already visible in Andromeda's halo are the remains of this process applied to earlier generations of infalling dwarfs. The most prominent of them, the giant stellar stream, is a vast arc of stars extending far into the halo, the remnant of a relatively large companion galaxy that fell in and was disrupted. Its stars now spread across a region of sky larger than the visible disk of Andromeda itself. Other streams are fainter, older, more dispersed, their parent objects long since completely absorbed. Each stream has a different orientation, a different age, and a different chemical signature, corresponding to the different properties of the dwarf galaxy that produced it. The discovery and mapping of these stellar streams is one of the active frontiers of Andromeda research, and the work is painstaking. Detecting structures so faint against the background sky requires careful imaging over wide fields, sophisticated techniques for removing foreground contamination, and long exposures that accumulate the dim light of stars scattered across enormous areas. But the effort is scientifically valuable because the streams are not just beautiful. They are records. By mapping their positions on the sky and modeling their dynamics working backward from where the stars are now to reconstruct the orbit and properties of the galaxy that produced them, astronomers can reconstruct the history of infall events, building up a picture of what has come in and when and from where. This is a fossil record of a particular kind. Not the fossils of organisms preserved in stone, but the fossils of gravitational events preserved in the positions and motions of stars, written across hundreds of thousands of light-years of space. The halo of Andromeda is an archive of its interactions, everything it has ever absorbed, still present in some form, dispersed but not gone, traceable by those with the instruments and the patience to look. The full satellite population of Andromeda, including the streams and diffuse halo material from past mergers, gives a picture of a galaxy that has been actively absorbing smaller companions throughout its history. This is how large galaxies generally grow, not primarily through internal star formation, but through the hierarchical merging and absorption of smaller structures, each one adding its stars and dark matter to the growing whole. Andromeda is larger than it once was. It will be larger still. In the halo around the visible galaxy, written in the positions of scattered stars too faint to see without careful effort, is the record of everything that came before the small companions, the dwarf galaxies, the infalling objects pulled in across billions of years, all of it present, still, dispersed and absorbed and quiet, part of something larger than they were. Sleep well, and good night. The dark matter halo of Andromeda is the dominant component of the galaxy's total mass, yet it is entirely invisible and its nature is unknown. These two facts together make it one of the most interesting and one of the most frustrating aspects of the galaxy to think about. What is known about dark matter comes entirely from its gravitational effects. It was inferred from the rotation curves of galaxies, the observation that stars in the outer regions of spiral galaxies orbit faster than the visible mass alone could explain. If only the visible matter were present, stars at the edges of a galaxy should orbit more slowly, the way the outer planets of the solar system orbit the Sun more slowly than the inner ones, following the same inverse relationship between distance and speed that Kepler described 4 centuries ago. They do not. They orbit too fast. The only explanation that has survived sustained scrutiny is that there is more mass than we can see distributed, not in a disk, as the visible stars and gas are, but in an extended spherical halo, contributing mass at every radius, keeping the rotation curves flat all the way out to the visible edge and beyond. This was not an easy conclusion to accept. When Vera Rubin and her colleagues published careful measurements of galaxy rotation curves in the 1970s, the implications were uncomfortable. Physics does not enjoy invisible things. It prefers, where possible, to account for everything in terms of known substances behaving in known ways. Various attempts were made to explain the anomalous rotation curves without invisible matter to modify gravity itself, to find some distribution of ordinary dim matter that could do the work, and some of these alternatives remain under active investigation today. But the case for dark matter did not rest on rotation curves alone. It was required to explain the formation of large-scale cosmic structure. The observed distribution of galaxies in the universe matches predictions from simulations that include dark matter and does not match simulations without it. It is constrained by the behavior of galaxy clusters, the pattern of fluctuations in the cosmic microwave background, and gravitational lensing observations. The evidence is abundant, and it points in the same direction. Most of the mass in the universe is something we cannot see and do not understand. What dark matter is, in terms of particle physics, remains unknown. It is not made of ordinary atomic matter, not electrons and protons and neutrons. It does not emit, absorb, or reflect light at any wavelength. It does not decay on any timescale that can be constrained by current observations. It interacts gravitationally and, possibly, very weakly through one of the other fundamental forces, but this weak interaction has not yet been detected in laboratory experiments, despite extensive searching. Experiments have been built deep underground to escape the noise of ordinary cosmic radiation tanks, of ultra-pure liquid xenon, crystals cooled to within a fraction of a degree of absolute zero, instruments of almost incomprehensible sensitivity, and they have searched for the faint recoil that a dark matter particle would produce if it happened to strike an atomic nucleus. They have found nothing that can be confirmed as a dark matter signal. Each non-detection is informative in the sense that it rules out dark matter particles with certain masses and interaction strengths. But the fundamental question remains open. Various candidates have been proposed over the years. Weakly interacting massive particles, known by the acronym WIMPs, were for a long time the leading theoretical candidate, motivated in part by a coincidence between the mass range that would explain dark matter observations and the mass range expected for new particles from theories that extended the standard model of particle physics. The coincidence was suggestive enough to drive an enormous experimental program. The WIMPs have not appeared. This does not mean they do not exist, but the most natural versions of the idea have been constrained severely and the field has widened. Axions, very light particles, originally proposed to solve a different problem in particle physics entirely, are now taken seriously as dark matter candidates and are being searched for with their own class of experiments. Primordial black holes, formed in the early universe before any stars existed, have been proposed and constrained and partially revived and constrained again. The list of possibilities has not shortened so much as it has spread out, becoming harder to hold in a single thought. This is a genuine open question, one of the large remaining mysteries of physical science. The galaxy we are looking at, the faint smudge in the night sky, is mostly made of something that physics does not yet understand. The majority of Andromeda's mass is not stars or gas or dust. It is an unknown substance distributed in a roughly spherical halo around the visible galaxy, shaping the orbits of everything within it, determining the fate of satellite galaxies and incoming intergalactic material, holding the system together against the general tendency of isolated objects to fly apart. The halo extends far beyond the visible disk, far beyond the spiral arms and the outermost detectable gas, out into a region that contains almost nothing that can be observed directly. The visible galaxy, the one that produces the faint glow detectable to the naked eye on a dark autumn night, is embedded within this halo the way a single lit room is embedded within a very large, dark house. The room is real and warm and filled with activity. But the house is larger and mostly dark, and its structure determines where the room can be and how it holds together. There is something interesting in that, and also something very calm. The universe contains mystery that is not threatening or urgent, just genuinely open, like a question asked in a quiet voice that nobody has yet answered. The dark matter in Andromeda's halo has been there for as long as the galaxy has existed, shaping it, stabilizing it, providing the gravitational framework within which all the visible activity has taken place. It has been doing this without our knowledge of its existence, without our ability to detect it, without any need for our understanding. For all of human history, people looked at the faint smudge in the sky and saw only what the light revealed. The dominant structure of the thing, the invisible architecture holding it together, was completely unknown. It is still, in the most important sense, unknown. We have measured its effects with great precision. We do not know what it is. This is worth sitting with for a moment. We are accustomed to thinking that science has, in the broad strokes, explained the physical world. And in many ways, it has the nuclear processes that power stars, the expansion of the universe, the genetic code that copies itself inside every living cell. The account is genuinely impressive. But dark matter is a reminder that the inventory of physical reality is not closed. The majority of the mass of the universe is something for which physics does not currently have an explanation. It is not a small, unexplained residual. It is most of everything. That the universe should be so constituted that the dominant component of its mass should be completely opaque to direct observation, completely unresponsive to the full spectrum of electromagnetic radiation that we have spent centuries learning to use as an instrument, is humbling in a particular way. It is not the humbling feeling of being small in a large universe, which is familiar and well-worn. It is the more specific and perhaps more interesting feeling of being embedded in a physical reality that the most successful scientific theories in history have not yet fully described. The darkness is not just overhead. It is everywhere, in every direction, constituting most of what is there, shaping everything, undetected. The detection of dark matter, either through direct detection of dark matter particles in laboratory experiments or through indirect astronomical signatures, is an ongoing research priority in physics. The search continues, and the field remains genuinely uncertain about what the next decade will bring. Perhaps a signal will appear in one of the next generation of experiments, and the long search will end with an answer. Perhaps it will not, and the mystery will deepen. The universe has not shown any particular concern for resolving itself on a timescale convenient to human science. In the meantime, the dark matter halo of Andromeda continues to do what it has always done: exert gravity, shape orbits, hold the system together. The stars orbit within it, the gas moves through it, the satellite galaxies circle within it, and the visible galaxy glows within its invisible embrace, entirely unaware, in the way that things that do not have awareness can be unaware of the dominant, invisible structure that makes it possible. The faint smudge in the autumn sky is mostly dark matter. It has always been mostly dark matter. You can look at it tonight on a clear night, let your eyes adjust, find the soft, elongated glow between the legs of Pegasus and the chain of Perseus, and know that what you are seeing is the smaller part of it, the luminous fraction, the visible activity embedded in something larger and darker and still unknown. It is there. Most of it is invisible. We do not know what it is. Sleep well and good night. Andromeda has always been there. It was there before the first human eye turned upward to find it, before the first hand reached up to point toward the faint smudge between the stars. It will be there tonight, after these words end, and the voice fades and the silence returns. Its light is still traveling outward in every direction from a trillion stars, some of it always heading this way, always crossing the dark toward a small rocky world that developed the capacity to notice it. There is nothing that needs to be concluded about Andromeda. It does not have a lesson it is trying to teach, a message it is carrying across the dark. It is simply a galaxy, doing what galaxies do, rotating, forming some stars, losing some stars, absorbing its satellite companions, sending light in all directions at the fastest speed anything can travel. It has been doing this for a very long time. It will continue doing this for a very long time after the last thought has been thought on this particular planet, after the last eye has closed for the last time on this particular night. We named it, of course. We could not resist. We saw a faint glow in the autumn sky, traced it into the shape of a chained princess from a story we had already been telling for centuries, and we wove the galaxy into our mythology before we even understood what it was. For most of human history, no one knew it was a galaxy at all. It was simply a cloud, a smear of light that did not resolve into individual stars the way other patches of sky did, and so it was called a nebula, a cloud, nothing more. It was only in the last 100 years or so that instruments became precise enough to settle the question. This was not a cloud inside our own galaxy, but an entire separate system, an island universe, as vast and intricate as the Milky Way itself, floating 2.5 million light-years away in the dark. The universe, overnight, became unimaginably larger, and Andromeda, which had been there all along, was suddenly something else entirely, not a nearby smudge, but an immensity, a mirror, another gathering of hundreds of billions of suns, held together by gravity and time. It did not change when we understood it differently. It was the same object it had always been. Only we had changed. Only our capacity to hold what it actually was had finally grown large enough to contain it. There is something worth sitting with in that. The thing itself was always there. The understanding arrived later, quietly, the way most important things arrive. There is nothing that needs to be concluded about Andromeda. It does not have a lesson it is trying to teach, a message it is carrying across the dark. It is simply a galaxy, doing what galaxies do, rotating, forming some stars, losing some stars, absorbing its satellite companions, sending light in all directions at the fastest speed anything can travel. The faint smudge in the night sky asks nothing of you except to be noticed, occasionally, on a clear night, when the conditions are right and the eyes have adjusted and the mind is still enough to take in something 2.5 million light-years away. You do not need to understand it fully to appreciate it. You do not need to hold all of what it is in a single thought. You can simply know it is there, the way you know that the night is there, present, quiet, enormously patient, indifferent to whether you look or do not look, unchanged by your attention or your absence. This is rarer than it sounds. Most things in a life ask something of you. They ask for decisions, for energy, for presence, for response. They arrive with weight and urgency and a sense that something must be done about them. Andromeda asks nothing. It does not know you are there. It does not adjust itself to meet your expectations, or shrink to fit your understanding, or expand to fill your need for something large. It simply is, completely and without apology, in the way that only very old and very large things can simply be. To look at it, really look, with the eyes adjusted and the mind quieted, is to be briefly in the presence of something that requires nothing from you. That is an uncommon feeling. It is worth seeking out. You do not need a telescope, though a telescope helps. On a dark night, away from the lights that have spread across the surface of this planet over the last century or so, Andromeda is faintly visible to the unaided eye. It does not look like much. It looks like a smear, a thumbprint on the glass of the sky, slightly elongated, dimmer at the edges than the center. It does not announce itself. But it is there that soft glow is the combined light of hundreds of billions of stars, crossing 2.5 million light-years to land softly in your eye. The fact that it looks so modest from here is a measure of how far away it is. Up close, if there were such a thing as up close for a galaxy, it would fill the entire sky. It would be the sky. Instead, it arrives at you quietly, uncertain of its welcome, not asking to be admired, just present. The light that reaches you from Andromeda tonight left the galaxy before your species existed. It has been travelling through empty space for all of human history and considerably before it. It has passed through the cold intergalactic medium without being stopped or scattered, crossing a distance so large that the word distance loses its ordinary meaning, and it has arrived here, softly, on this night, in this room, finding its way to eyes that close a little more easily for having thought, for just a while, about 1 trillion quiet stars turning in the dark. Think about what that light has outlasted. It left Andromeda before the first stone tools were knapped, before fire was understood, before language shaped a thought into a form that could be passed from one mind to another. It was already well into its journey when the first cities rose and fell, when writing was invented and lost and reinvented again, when every empire that has ever called itself eternal rose and crumbled and was replaced by another empire equally convinced of its permanence. All of that, all of it, occurred while this light was in transit. And now it arrives, this particular collection of photons, on this particular night, at these particular eyes, which are tired and ready for sleep, and perhaps a little quieter than they were an hour ago. There is nothing mournful about this. The scale is not crushing, not if you let yourself settle into it rather than resist it. The vast age of the light does not diminish the moment of arrival. If anything, it deepens it. The specific collection of light years and accumulated human history that had to occur to produce this exact moment, you, here, in the dark, looking up or thinking about looking up, aware for just a moment that something 2.5 million light years away has been travelling toward this precise point in time, that collision of the enormous and the intimate is not diminishing. It is quieting. It sets the mind's smaller agitations gently to one side. In roughly 4.5 billion years, Andromeda and the Milky Way will collide. This is not a catastrophe, or not the kind of catastrophe the word implies. Galaxies are mostly empty space, and when they meet, they pass through each other slowly, over billions of years, like two swarms of fireflies interpenetrating in the dark. Stars almost never actually collide. The galaxies will distort each other, pull each other into long tidal streams, orbit each other, and eventually merge into a single larger galaxy, something that astronomers, with characteristic understatement, have already named Milkomeda. This will happen long after the Sun has expanded and dimmed, and the Earth, in whatever form it still takes, has long since grown cold. It is nothing to worry about tonight. But it is something to know that even the slow wheel of Andromeda across the autumn sky, is not permanent. Everything is in motion. Everything is in process. Even galaxies arrive and merge and become something new. Tonight, though, it is simply there. 2.5 million light-years away, rotating slowly, forming some stars and losing others, sending light in every direction into the dark. Some of that light is heading this way, always heading this way, crossing the intergalactic silence toward a small world where creatures developed eyes and curiosity, and eventually the habit of looking up. It has always been there. It will always be there. And nothing about it needs to end. Sleep well and good night.